Hello everybody, welcome into another lesson. So today is going to be starting a two-part lesson on graphing polynomials. And today specifically we're only concerned with the end behavior of a polynomial curve, which is going to help us in the next lesson when we go to totally graph polynomial functions. But I'm starting with one that we all know, f of x equals x to the second. And as a side note, notice this brand new coordinate grid I got. No more hand-drawn graphs. Isn't that nice? I can actually make it nice and even and make it look like it's supposed to. But anyway, we have f of x equals x squared. We should all be familiar with this. Well, you notice from the vertex at 0, it rises to the left and it rises to the right. That's exactly what it does. It's an even power function. Now, what if, let me do this here, what if instead of x to the second, we raise it to the fourth power? So now we're going to graph f of x equals x to the fourth. What would that look like? Well, of course, at 0, when x is 0, you'll still have 0, 0, right? Now, let's say one of these units on the graph here, on the coordinate plane, is worth 2 units. There's a reason for that. So when x is 1, y is 1. But what about when x is 2? It's all the way up to 8. So 2, 4, 6, 8. No, actually it's 16. I'm sorry. I was thinking of the third power. 10, 12, 14, 16. And then, let's take negative 1 to the fourth. You'd still get positive 1. Then if I take negative 2 to the fourth, you would also get positive 16. Now let's connect the dots and draw this here. You go to connect that, what do you have? It looks almost parabolic, doesn't it? It just seems to get closer to hugging the y-axis. This is what the graph of f of x equals x to the fourth looks like. It also rises to the left and rises to the right. Let's do one more of an even power. Then we'll go on to odd powers. Let's say here I take f of x equals x to the sixth power, right? So x, it's going to go to the sixth power. This time one of these units is worth 8 units for the sake of our graphing. So of course 0 to the sixth is still 0, so we'll get the point 0, 0. 1 to the sixth is 1, that'll go right here, but what's 2 to the sixth? That's 64. 2 to the sixth is 64. And then negative 1 to the sixth would be positive 1. And then negative 2 to the sixth would also be 64. So let's go ahead and connect the dots and draw this here. And what do you get? You get another curve that resembles a parabola. So again, it rises to the left and rises to the right. And if you continue trying to do x to the 8th, x to the 10th, x to the 12th, what have you, any even power for a polynomial, you'll get the same result. If the coefficient on the polynomial is positive, in this case it is, it's a positive 1, the same would be true if it were positive 2, positive 1/2, what have you. You would just have a shrinking or stretching factor, but it would be similar. If it's an even power, and the leading coefficient is positive, the curve rises to the left and rises to the right. Now, let's shift it a bit here. Let's just change this up a bit. If I take this and say f of x equals negative x to the fourth, so now we have a negative coefficient on the x to the fourth term, right? Well, let's put in 0 for the x. You'll still get 0, 0. And one of these units will be worth 4 units, just for this, or 2 units rather, for the sake of graphing. If I put in positive 1 to the 4th, that would give me 1, and then I negate that, I'll actually end up getting negative 1. So there's 1, negative 1. If I put in positive 2, I should get negative 16. And then if I put a negative 1 to the 4th, I should also end up getting negative 1 for my point here. I should get negative 1, negative 1. Put in negative 2, I should end up getting negative 2, negative 16. If you draw the curve, what do you get? You get a very similar shape to f equals negative x squared, right? It looks almost similar to f equals negative x squared, only this is f of x equals negative x to the 4th. So if you have an even power polynomial and the coefficient on the leading term is negative, it falls to the left and falls to the right. So that's something to understand about even power functions graphs. If the coefficient is positive, it rises to the left, rises to the right, and pretty much looks like a parabola, almost like f of x equals x squared. If the coefficient is negative for an even power, it falls to the left and falls to the right. Okay? Now, let's move on to odd powers. And if we did f of x equals negative x to the 6th, we would get roughly the same thing. Alright, now, you're probably wondering, okay, we've done even powers, what about odd? Well, here we go. F of x equals x to the 3rd power. So what's that going to look like? Let's take f of x equals x to the 3rd power. Well, if you take 0 to the 3rd power, you still get 0. You'll have the point 0, 0. Now, what if I take 1 and raise it to the 3rd power? Every unit will be worth 1 in this case. But 1 to the 3rd power is still 1. What's 2 to the 3rd power? That'd be all the way up to 8. Alright, now, what if I took negative 1 and raised it to the 3rd power? I would end up getting negative 1, so you'd have the point negative 1, negative 1. Now, what if I took negative 2 and raised it to the 3rd power? I should get negative 8. So I should get the point negative 2, negative 8. Now let's connect the curve here. Let's show you what a cubic function graph looks like. Alright, and what do you know? We have a nice cubic function graph. Why is that not coming off? That's going to be annoying. Alright, so this is what the curve of f of x equals x to the 3rd looks like. From the central point, 0, 0, you can't really call it a vertex because it doesn't like bow down in the middle and then rise one way and rise another way. From the central point of this curve, it falls to the left, but it rises to the right. So it's going to fall to the left the further left you go, and then it's going to rise to the right. Now, what if we do f of x equals x to the 5th? So let's take, this time we'll do f of x equals x to the 5th power. Another odd power function, f of x equals x to the 5th. Well, let's put in 0, of course. You'll still get 0. So 0, 0 is a point. We'll make one of these squares worth 4. We'll make it worth 4, okay? If I take 1 and raise it to the 5th power, I'll get 1. Alright, what if I take 2 and raise it to the 5th power? That would put me all the way at 32, right? 2 to the 5th power is 32. Now, what if I put in negative 1 to the 5th power? I would get negative 1, right? So that's going to put me right here at negative 1, 1. If I take my negative 2 and raise it to the 5th power, I should get negative 32. 32, so that should put me right there at negative 2, negative 32. Then I'll just go ahead, connect my curve again, right? And what do you know? I got a curve that's almost identical to that of f of x equals x to the third. It falls to the left, but rises to the right of the central point. Falls to the left, rises to the right. And if we were to try and take x to the 7th, we would find the same thing. We would get the same type of shape at least if we did x to the 7th and x to the 9th, x to the 11th, so on. So whenever you have an odd power polynomial with a positive leading coefficient, it always falls to the left but rises to the right. Now let's do a couple with negative coefficients. Let's do some negative coefficients here. So we'll do f of x equals negative of x to the third. So this time we have f of x equals negative x to the third. So we have a negative leading coefficient, and it's to an odd power, it's to the third power. So put in 0 for x, well, you'll still get 0, 0. And every unit in this case will be worth 1 unit. So if I put in positive 1, I'm actually going to get negative 1 since there's a negative sign in front of that. If I put in positive 2 for the third power, I'd actually end up getting negative 8 in this case. So there's 2, negative 8. Now what if I put in negative 1? Well, negative 1 to the third is negative 1. If you negate that, you'll actually end up getting positive 1. If I put in negative 2 for x, well, negative 2 to the third is negative 8. Negate that, you actually end up getting positive 8. All right, then you're just going to go ahead and connect your curve. And what do you see? It's flipped around from the central point. Since we've negated the x to the third, it's actually flipped around from the central point. This time, if we want to evaluate the end behavior, it rises to the left and falls to the right. And if we try to do f of x equals negative x to the 5th, we're going to get something almost identical, curve-wise. Same with negative x to the 7th, and so on. So, if you have an odd power polynomial and the leading coefficient is negative, it rises to the left and falls to the right. So that is something to keep in mind. So, recapping here. Let's just do a brief recap. If I have an even power polynomial with a positive coefficient, any even power polynomial with a positive coefficient, it's going to rise to the left and rise to the right, giving you pretty much a parabolic shape, almost like f of x equals x squared. If I have a positive polynomial, a positive degree polynomial, I should say, but it's got a negative leading coefficient, then it's the opposite. You have a reflection in the x-axis, which causes it to fall to the left and fall to the right. Now, getting to odd power polynomials, if you have a positive coefficient on an odd power polynomial, then it's going to fall to the left and rise to the right. And then if you have a negative coefficient on an odd power polynomial, it'll rise to the left and fall to the right. So that's just general basic shapes of polynomial function graphs. Next lesson, we'll get into more detailed graphs. We'll talk about plotting intercepts and whether or not the curve crosses through the intercepts or just touches the x-axis at that point. We'll talk about local maximums and minimums. We'll talk about turning points, all those kind of things that will help us to graph a polynomial function without a graphing calculator. So I hope everyone has a great night. Take care.